Today's episode explores how AI is reshaping both the digital and physical worlds. We start with a hard look at generative search, where Google's AI overviews and Gemini are changing what users see, what sources get cited, and how stable search results really are. Then we dive into new theory on deep transformers, revealing how noise can synchronize representations as models scale. Finally, we move into medical innovation, where CT-informed Gaussian splatting helps bronchoscopies track breathing motion with remarkable precision. Let's explore the first paper, How Generative AI Disrupts Search, an empirical study of Google Search, Gemini, and AI overviews. This paper quantifies how Google's AI overviews, AIO, and Gemini Flash 2.5 alter web search retrieval at scale using 11,500 query benchmarks spanning Orcus, Amazon Retail, ELI5, natural questions, localized queries, and debate-style prompts, plus 2,712 time-sensitive queries for political and trending topics. AIOs are generated for 65.6% of all benchmark queries and 51.5% of representative ORCAS queries, with prevalence rising sharply for interrogative, informational, and longer queries. For example, 94.6% of ELI5 and 93.8% of political queries trigger an AIO, while only 17.4% of Amazon retail queries do. Across Google Search, AIO and Gemini, retrieved URL sets are highly divergent, with average Jacquard similarity only 0.11, 0.18, and RBO never above 0.27. AIO and Gemini are the least similar pair. Traditional SERP disproportionately cites popular and institutional domains, whereas generative search shifts toward less popular and more Google-owned sources, especially YouTube and Google.com. Notably, websites blocking the Google Extended Crawler are significantly less likely to be cited even in AIOs, despite Google's claim that AIO access is unaffected. Consistency is weak. 2 runs of the same query, or minor edits such as contractions and question marks, produce materially different source lists, and AIO is less robust than SERP. For high-stakes political queries, AIO and Gemini increasingly cite lower credibility sources and sometimes adopt a stance. 33.4% of AIO debate responses and 5.6% of Gemini responses begin with explicit, affirmative, or negative framing. The authors release code and a public benchmark to study generative search drift and argue that publisher revenue sharing and credibility-aware retrieval are necessary to stabilize this ecosystem. Let's explore the second paper, Stochastic Scaling Limits and Synchronization by Noise in Deep Transformer Models. The paper derives the first quantitative stochastic scaling limit for transformer residual stream dynamics that includes both softmax self-attention and randomly initialized MLP blocks. For fixed token count n, depth L infinity, and width M infinity, it proves pathwise convergence of the discrete layer map with layer norm on ST1 to a coupled interacting SDE with deterministic mean field attention drift plus a common non-interacting Gaussian noise field generated by the wide MLP limit. The error is bounded by Cn, exp, Cnt, log L, L plus 1, M, improving to C exp C T log L, L plus M minus 1/4, under phi belongs to C, infinity, and the deep and wide limits commute. The limiting field is identified via a zonal covariance kernel. Kxy equals kappa xy with a Karhunen-Loew expansion on the sphere, and the induced Eulerian limit is an SPDE on P1-ST1 with Laplace-Beltrami diffusion and transport by common noise. In the large N regime, the empirical measure converges in expected supremum W2 at rate RD n equals n1/2 for d is less than 4, n1/2 log 1 plus n for d equals 4, and n2d for d, fire, yielding a fully quantitative triple limit result for transformer residual dynamics. The second main contribution is a synchronization by noise theorem for the limiting McKean-Vlasov system. Under an explicit non-oddness condition on the MLP random field and a coercivity constraint, lambda equals d1 kappa 1 d3 kappa 1 is less than 0, the interaction energy E beta mine equals 1/5 A beta E beta minus X Y ddm minus dm minus decays exponentially in expectation. E beta is less than or equal to expect. Epsilon plus lambda E beta 0, with lambda is less than 0, implying convergence to random point attractors, and L2 synchronization. For ReLU, they compute lambda 1 equals minus sigma 2 plus 2, sigma W 2d1 divided by 4d, and lambda minus equals minus sigma 2 plus 2, sigma W 2d1 divided by 2d, showing noise-induced collapse, is generic for standard Gaussian MLP initialization. Numerical experiments on n equals 64 tokens, d belongs to 564,128, L equals 150, and activations ReLU, SILU, sigmoid, and tan confirm that bias strengthens synchronization. Sigmoid collapses fastest, and attention can either amplify or resist the noise-driven contraction. Let's explore the third paper, Stop Holding Your Breath CT-informed Gaussian splatting for dynamic bronchoscopy. Stop Holding Your Breath reframes bronchoscopic video to CT registration as a patient-specific respiratory inference problem rather than a static alignment problem. The key observation is that paired inspiratory and expiratory CT scans, already acquired for planning, define a one-dimensional deformation manifold for the airway. The method registers these scans once, then models each frame by a scalar breathing phase alpha in 0, 1, instead of learning unconstrained per-frame deformation. This phase drives a CT-derived airway mesh, and a mesh-anchored Gaussian splatting representation inherits the mesh deformation through barycentric anchoring, so Gaussian positions, orientations, and covariances remain anatomically consistent. A lightweight estimator infers breathing phase directly from monocular RGB bronchoscopy, using a cosine-based bounded parameterization with a small linear gradient leak to avoid saturation at full inspiration and expiration. The authors also introduce Respire, a physically grounded simulation benchmark built from 9 COPD gene cases with paired CTs, grad icon registration, VMTK centerlines, and blender cycles rendering with subsurface scattering, specular wet surface glare, and camera light exposure variation. Respire provides per-frame ground truth for geometry, pose, depth, breathing phase, and deformation, filling a major evaluation gap in bronchoscopy. On Respire, the full method reaches 27.37 PSNR, 0.821 SSIM, 3.2 mm depth RMSE, 0.88 delta is less than 1.25, breathing phase MAE 0.158 with Pearson R equals 0.833, and 1.22 mm target localization error, within the clinically relevant to 3 mm biopsy tolerance. Relative to bridge splat, depth RMSE drops by 94%, and training time falls from 383.4 minutes to 17.4 minutes, about 22 times faster. The main novelty is converting respiratory motion into a low-dimensional, CT-constrained latent variable, eliminating breath hold protocols while improving geometric fidelity and runtime. That's a wrap on today's AI paper highlights. Thanks for watching.